chat. So, welcome to today's session of the lecture overview and Q&A session for the operating systems course. So the two lectures you were supposed to watch last week were concerned with two different topics. So in lecture 12 from the week before, we already had a look at regular scheduling algorithms for single processor systems. And in lecture 13, we took a closer look at specialized scheduling algorithms that are suitable for use in what we call real-time systems. So systems in which it is important to have a timely response to some external event. Mind that the real-time scheduling, this lecture 13, is not relevant for the exam. There's a lot of math inside, so it might be very, very nice to have it in the exam, but then I guess you would hate it. So this is not relevant for the exam. So for real-time scheduling, we defined real-time problems, we looked at deadlines, we looked at scheduling in general, and then we took a closer look at two different very common scheduling algorithms. One is rate monotonic scheduling, and the other was earliest deadline first scheduling. And then in lecture 14, we had a closer look at input-output. So far, we looked at processes and semaphores and synchronization and all that stuff, but we didn't really consider what happens if your computer has to talk to the outside world, no matter if it's a disk, for example, or some other I/O interfaces. So first we had a look at how I/O devices actually communicate with our processors. So how do we interface to them? So we had to look at buses. We had to look at methods to transfer asynchronous information using interrupts. We had to look at direct memory access and also obviously at addresses. So at which addresses can I actually talk to my devices here. Then we took a look at two general different modes of talking to an I/O device. One was polling, the other was running it with interrupts. And then we took a look at what's concerned in the system software in the kernel itself. So we have device drivers that are responsible for communicating with our devices. And we took a look at the different layers of the I/O subsystem in an operating system kernel. Then we took a bit of a look at how all this works in Unix. So which device abstractions we have in Unix, which device classes exist. And finally, we had a closer look at buffering and scheduling of I/O. So for real-time problems, we took a look at what might happen if you miss what we call a deadline. So if you're, doing some computation on your device, you provide a result. So usually you have an input from like a sensor or the network, and you need to react in a given, amount of time. And what happens if you don't do this? So if you, what we call miss this deadline here. So we classified our real-time systems into three different classes here. So we had soft real-time systems, which means that the obtained result, so the reaction of the system is useful even if your deadline was missed. So if it was obtained after the deadline has passed. Something like this might be a video or audio decoder, for example. So you usually want to have like 60 frames per second. And if your computer is too slow, or your video has too high a resolution for your video card and computer to manage this, then maybe you have a bit of stuttering, but still you need the intermediate results because all the subsequent video frames depend on this information you decoded in between. So video audio systems are typical example of soft real-time systems. Firm real-time systems, some people only classify soft and hard. We took this third classification in here. So firm real-time system means that the result is useless after the deadline has passed, but nothing bad happens. And then there's hard real-time system. And this means if the deadline passes without the system reacting, then some damage can occur. So for example, if you have a car and you use your anti-lock braking system and it doesn't react within 200 milliseconds, but in the special case, it reacts within 2 seconds, you maybe, steer off the road, hit a tree or whatever. And that's obviously something you don't want to happen. And the question is, how can we analyze how much compute time a process or a program needs, or how can we analyze if we actually are going to meet a certain deadline? So we took a look at worst case execution time, or WCET analysis. So if you look at that diagram on the lower left here, you see the possible distribution of execution times of the program. So this is a histogram. So for example, you have discrete times, maybe in clock cycles or milliseconds or whatever you want to have here. And then you just count the occurrences if you run your program with different input parameters. And then if you look at the histogram, there's a minimal time. So there's some cases which have the least amount of time that's actually has any value in that diagram here. And you have the maximum time, which is the worst case execution time of the system. So that's the time you need in the worst case. So no matter what happens with your software, which input parameters you get, how many loop iterations you run, you cannot take longer than this worst case execution time. The problem is that this real worst case execution time is very hard to figure out, because what happens is a combinatorial explosion. So if you have like 100 input parameters to your program, and each of these can influence that, then of course all these, you have to test all these combinations of these. So in essence, you won't be able to do this. So the only thing we can do is we can try to obtain an estimate for the worst case execution time, which has to be as large or larger than the real worst case execution time. So you have to provide a safe estimate. And you want this estimated worst case execution time to be as close to the real worst case execution time as possible. So there's commercial and open source analysis tools, and the lower your difference between the estimate and the real worst case execution time is, then you waste less CPU cycles, for example, because what you have to plan for when you want to keep all your deadlines, for example, you select a CPU frequency to run it, is the estimated worst case execution time. So you want to create what we call these tight bounds between the estimate and the real worst case execution time. And you definitely want to be on the safe side here. Right, so we don't go into details how all these analyses work. With today's processes, they have to be very complex. So these analyses have to consider things like cache effects, pipelining effects, and so on. These would be definitely parts of a master's course, for example, on what we call non-functional properties. So we took a look at rate monotonic scheduling as a scheduling algorithm first, and we've seen there's a number of requirements for rate monotonic scheduling. The first requirement was that we have preemptible tasks. So all tasks are preemptible at any time. Then we make a simplification that only compute time is a relevant resource, so we don't consider I/O here. Then we stated that all tasks have to be independent, so there is not any synchronization happening between tasks that might hinder one task from continuing. Then we said that all tasks have to be periodic here, so they have to be executed with a certain time period over and over again. And the fifth simplification was that the relative deadline of a task is equal to its period. Now you might think that we're oversimplifying things here, but that's not the case, because this is something that happens in a large number of real-time systems. And then we looked at what we call schedulability. So can we actually, given a number of tasks in our system, can we build a system that is able to keep all of our real-time constraints, to keep all of our deadlines? So obviously, what we call the utilization of the system, which is the sum of all the essentially times divided by the tasks. So essentially the sum of compute time used in our system, this has to be less or equal than 1. If we would require more compute time than we have available on a uniprocessor system, obviously we would not be able to execute all the tasks in our system. So this is necessary. So obviously our utilization needs to be less than or equal to 1. But there are some cases where with a utilization less or equal to 1, we can still not find a schedule for this. And we found out that no deadline violation happens if the following condition holds. So the utilization is less than the number of tasks multiplied by the m's square root of 2 minus 1. So essentially for m going to infinity, this means that the utilization must be less than or equal 0.69 something. And usually what to keep in mind here is that the utilization should be less than or equal 0.7. This is the safe side. And if you can prove that this utilization is less or equal than 0.7, then you know this set of tasks is schedulable on your real-time system, so you won't ever miss a deadline. This is a hard guarantee, which is an important result here. The other scheduling algorithm we took a look at is earliest deadline first scheduling. So in EDF scheduling, we look at tasks which are ready and sort them in order of their absolute deadlines. So the task that has to deliver its result at the earliest absolute point in time. So the task for which the next result needs to be available. This is the one that comes first. And if the first task in the list then has an earlier deadline than the currently running task, then the running task is immediately preempted. And we have seen that if a schedule exists, which is able to keep all deadlines, then EDF can create a schedule that keeps all deadlines. And this is also called that EDF is optimal. But of course, with some constraints. So again, like with rate monotonic scheduling, we need independent tasks and we need dynamic priorities. So these dynamic priorities change according to the deadlines of the tasks in our systems. And if we consider periodic tasks with EDF scheduling, then the following holds. If the utilization is less than or equal to 1, then EDF scheduling always finds a valid schedule without missing deadlines. So EDF in this respect is a bit better than rate monotonic scheduling, but of course it requires to know the absolute deadlines always, which is usually the case, and it requires that we can change these priorities at runtime. So implementing this at runtime is a bit more overhead. By the way, for all of these real-time scheduling algorithms, we always assume that the overhead of the operating system itself, so the time it takes to do the scheduling, so context saving, selecting a new process, context restoring and switching to the new process, that this is negligible in comparison to the time the tasks execute. If we would have to consider this, then this analysis would get much more complicated. So the real world can actually be a bit more complicated than these theoretical analysis. Now, I'm not going to talk a lot about these real-time scheduling systems. There are complete courses on this. So if you're interested, feel free to ask around, and I can give you some links to additional information on real-time systems. And as I said, real-time scheduling, this lecture 13 is not relevant for the exam. But of course, we'll summarize what will be relevant for the exam in the last lecture, also Q&A slot, before the end of the semester. So in lecture 14, we talked about I/O devices, and we've seen I/O devices are interfaced to the CPU. So the CPU can request data from an I/O device, can send data to an I/O device. And this is usually done, of course, this here is a simplification using what we call a bus system. So a bus system connects one or more CPUs with all the other components in your system. This can be main memory, and also the different sorts of I/O controllers, like we have a keyboard controller, video controller, disk controller, and maybe an Ethernet controller here. And usually a device, the CPU can read and write from devices or memory. And in order to distinguish which component was actually accessed here, these devices have addresses. So for example, main memory, if we have a 32-bit addresses on the bus, main memory could maybe use the addresses from 0 to hexadecimal 3, FFF. This would essentially mean that's the lower gigabyte of our memory address space. And then we could have, for example, a video controller at that address here, a disk controller at that address 0x670s, and an Ethernet controller at 0x870s. In early PCs, you had to configure all the addresses of the peripheral components by hand using switches or jumpers, so short pieces of wires on the peripheral cards. That was very tedious, and if you made a mistake, usually your system didn't work. On modern computers using PCI buses and lots of onboard peripherals, this happens automatically. So PCI, PCIe have a sort of an automatic configuration, and then the CPU's task or the operating system's task at startup is actually to look at all the possible addresses to figure out which device is there, and then essentially to configure the respective driver for the device to use the address the device was detected at. Now, CPUs can read and write from memory and devices. But there's also other ways in this system to communicate. So whenever you send a task that takes a bit longer, or there's something asynchronous happening which you cannot expect in advance, then it would be a waste of compute cycles to just wait for it and request from the device over and over again, like, is there something new? No. Is there something new? No. Is there something new? No. Is there something new? Yeah, finally, yes. So essentially what you should do is continue computing whatever your application is doing. And then whenever something happens on the outside, so from your peripheral, you get an interrupt, for example. So for example, when a key is pressed on the keyboard, your keyboard controller would send you an interrupt, and then you could handle this interrupt by retrieving that key and acting on that key press. Or this controller could notify you when there's a new block that was read from a disk, which can take on a real physical hard disk with heads and stuff, so not an SSD, which can take milliseconds. And of course, you can do lots of computation in this amount of time instead of waiting for it. And some sophisticated devices that have to transfer a large amount of data, like disk controllers or Ethernet controllers, can also directly transfer data from and to main memory using the bus without pushing each and every single byte through the CPU and then to memory or the other way around. So this is what we call direct memory access. So this is our blue arrow here. So essentially the CPU can instruct using a so-called DMA controller, can instruct the peripheral device, like, if this data packet finally arrives, you can send me an interrupt, but you can also start transmitting all that data to memory automatically, so the CPU doesn't have to do it, well, more or less manually. So we took a look at ways to interface from software to peripheral devices. So as I said, it's usually quite a waste of time if I just request over and over again, like, is there something new? No. Is there something new? No. So this is what we call polling. Polling is essentially just active waiting in a loop, like shown on the right-hand side here. So essentially, you just run a number of times, and this while loop here in the upper code on the right-hand side just waits until our printer says it's ready, and then finally we write a character. Now, while we run this while loop, and the printer can be slow, obviously, oh well, we're just wasting CPU cycles, we're just twiddling thumbs, and so essentially we're wasting time. So with interrupts, I can actually send off the request to a printer, and then when this printer has printed its character, then the printer sends an interrupt, and then our CPU actually changes its context from whatever it's doing at the moment to what we call the interrupt handler. So the piece of code inside of your operating system, which is piece of the device driver, that is responsible for handling all these asynchronous notifications here. And so the interrupt handler is the piece of software that then communicates with the IO devices. So if we have an interrupt handler for a printer, for example, and the interrupt comes in, then our interrupt handler knows, okay, a character has been printed, so I can safely send the next one without checking again in the printer what's going on. And then I can just return from that interrupt handling routine and continue with what has been done before. So either executing an application program or maybe code inside of the operating system. So in general, it's preferable to do interrupt-driven IO, but interrupts have a higher latency. So if I do polling and nobody interrupts me, then it just takes a cycle or two until I can react to the status change in the while loop in the upper listing, and then I just fall through and can directly send this. Whereas with an interrupt, I have to save all my context because I'm executing code in the middle of the execution of another program. So I'm not allowed to disturb that program's information. So I need to save all my processor registers, for example, and maybe other contexts like page tables in the MMU. This takes quite a bit longer than polling. So some drivers that have to be very fast do polling for short amounts of time, but this can be very, very, very problematic. So in early Linux versions, for example, you had polling for very fast old hard disks with IDE interfaces. And this polling turned off the interrupts because it didn't want to be disturbed. So people found out, I think that was a Linux 1.something kernel version. I need to find out which one it was. So people found out if they do lots of hard disk operations on their IDE hard disks, actually timer interrupts got lost. And if timer interrupts got lost, your real-time clock actually was lagging behind. So after lots of disk operations, actually your computer had the wrong type. And that was pretty interesting. So there's a question. When sending a command to an I/O device by writing to an address, does the device at least send a quick acknowledgement on the bus that the write was performed? Or does the CPU send a write into the void, hoping to receive an interrupt later? That's another question I have to answer with it depends. So it depends on the bus system you use. So there are, like on old 8-bit processors, for example, usually you just write things and hope it works. And usually it does, because you configure the timing in your system that all your peripheral devices are fast enough to receive all the requests from the CPU, so written from the CPU in real time. So if you look at an old Commodore 64, essentially you have like a bus cycle, and in each of these 1 megahertz bus cycles, you could write 1 byte of data, and the peripherals were matched to this, so they could read 1 byte of data per cycle and process it. In more modern devices, like on PCI buses, but also maybe on older devices like the 68000, you actually have what we call handshake. So essentially you send some piece of data, and then when this piece of data was received, maybe by a slow I/O device, then you got something back we call an acknowledge, so a special signal here. And only when that acknowledge was received, you could continue operating. So it really depends on the hardware of your system, on the configuration of your bus system. You can have both, but usually one or the other, but not both in one system. All right. So you've all installed device drivers, I guess, in your life before, no matter from Linux or Windows. So what's a driver? A driver is essentially part of the operating systems, though it does not have to come with the operating system, but it can be provided by a third party, like by a manufacturer of a plug-in card. And this device driver serves as a unified interface for devices. And what you usually want to have is a driver for a class of devices. So you don't want a driver for each and every separate different hard disk out there, but devices conform or should conform to certain protocols. So like each SATA disk should behave identically. So you only need one driver for SATA disks and not one from Western Digital and the other from whoever still manufactures hard disks. Actually, there's not that many companies left. And drivers provide a generic abstracted interface to a device, to applications. So applications can use system calls. We've seen open, read, write, close, and so on. And this generic interface allows applications to be written independent of specific devices. So I don't especially need to know the type of my hard disk attached to my system. I mean, for hard disks, we have further abstractions like file systems. I don't need to know the type of my Ethernet controller in order to send TCP/IP packets. So this is all abstracted. And so our I/O system is constructed in layers, and an I/O request travels down from user mode via the kernel. So you execute a system call like read or write, and then this request travels through the kernel. The kernel figures out this is an open file number 5, which is related to a certain device. So it hands over this data to the device driver, and then the device driver hands off the request to the hardware and receives either data or error codes back using interrupts. And these responses then travel up in the other direction. And we've seen most system calls are blocking. So when we operate a read, so we only return from that system call when we traveled down these layers, and the information we wanted travels up these layers again. So there's another question. Is that the case in practice? I know with computer mouses or mice, that's a good question in itself. Some work with Linux and some don't. So I assume there must be some variation. So in general, I think you refer to the general abstract interface. So in general, if you have a USB mouse, it should immediately work with Linux for its basic functionality. So for USB, there's a substandard in USB called HIT, the human interface device. There's one class for keyboards, there's one class for mouses or mice, and another for joysticks, and so on. And usually, at least the basic functionality of a mouse, like moving and having like 2 or 3 buttons and maybe a scroll wheel, That's what's specified in that standard, and that should work out of the box with any Linux device or Windows or even Mac. If you have special functions like additional buttons, or you can have a RGB LED on your mouse or whatever, I've seen one with a built-in calculator and display for whatever reason, then this is outside of the standard functionality. So if you need functionality in addition to the basic functionality provided by the driver, then you might actually need a specific device driver. But I haven't seen a mouse that didn't work with Linux for quite some time. So usually there's no specific mouse protocols used that don't follow the USB human interface device protocol. With wireless mice, that might be different. So because sometimes you have very specific wireless adapters, and there's in general two classes of wireless mouse adapters. So one, so usually you just get a USB dongle, and usually one class just emulates a USB wired mouse, so a human interface device. So this should look no different to a mouse with a wire, a USB mouse. And there are some others which have Bluetooth controllers. So they communicate to the host using Bluetooth. So the USB dongle you get is a little USB Bluetooth transceiver. And for these, not all of these are supported. And there might be some exotic proprietary solutions which use something else on USB. I haven't seen those, but then I don't buy all these fancy expensive mice, but only like 100 krona mice I buy in the shop. So these might be rare cases where the wireless transceiver actually has no driver. But usually these wireless transceivers cheat a bit and just emulate a USB mouse device or a USB human interface device. So most should work, and if there's an exotic case, that could be. Another question on USB. Are USB hubs part of the standard? Yes, they are. So USB hubs are definitely part, so because otherwise you would need separate USB controllers on your main board. So usually what you have on your main board is already some sort of hub for providing like the 6 or 8 or how many USB ports you have on your board. Some UEFI settings fail to recognize USB devices through SIM hubs. Yeah, that's a problem with standards compatibility. So if you buy some cheap stuff from some dubious sources on the network, then sometimes the timing might not be right. So this enumeration of IO devices, this takes a while. And if your BIOS, for example, doesn't really wait, or UEFI waits for the time, that's the maximum time available, then maybe some replies come too late, or some hubs maybe react too slow, so they violate the standard. So USB problems because there's so much pretty badly implemented hardware out there. And of course, there might be bugs in the UEFI implementation. So I had this problem on a Raspberry Pi. So there was a nice USB support library, and USB is a complex standard. So you don't want to write any USB driver yourself. It's horrible. And so you're pretty happy to use USB code that's already available. And there was a piece of code available for when I did my port of the little Smalltalk 80 operating system 2 years ago, actually. And I happily used this in the beginning on an original Raspberry Pi, which had like 2 USB ports, one for a keyboard, one for a mouse. That's nice. And then I tried to use it on a Raspberry Pi Zero, which only has one USB port. So if you want to connect a keyboard and a mouse, you need a USB hub. And my code stopped working because this USB driver didn't support hubs. So essentially, I had to upgrade the whole infrastructure behind this to a new version of USB drivers, a completely different one, actually, though written by the same person, that actually was able to support hubs and was like 3 times the size of this original USB code. Okay, so once you're into Linux, the hub works fine. So maybe Linux just applies different timing parameters here, so waits a bit longer for hubs. So in Linux, UEFI might just be closer to the standard timings, for example. So Linux actually, if you look into the kernel sources, has a large list of what we call blacklisted devices. So devices that violate the standard. And these devices require special handling in the device driver. So people really found this out usually by yeah, buying a device that doesn't work with Linux and then hacking the driver. And then usually this device is entered in such a blacklist in order to make it work with Linux. That's a difference with Windows drivers. So when you buy a specific device, you usually get a whatever CD, USB stick, or download address nowadays with drivers. And then, of course, these drivers specifically for your whatever blarf manufacturer USB special mouse, then these have all the quirks built in, whereas Linux has a generic driver model and then has to build in all the little fixes, and it figures out using the blacklist if it has to apply fixes. So usually every USB device, for example, has two ID numbers, a vendor ID and a device ID. So the vendor ID is like Logitech or Cherry or whoever is building your mouse. Intel, for example, has a vendor ID of 8086. Well, that's a nice coincidence, right? Because Intel defined the USB standard, and others have others IDs. So these are 16-bit numbers, and then each device should have its own number. So the mouse you have would have one of these 16-bit device numbers assigned to the vendor. So each vendor has its own 16-bit address space. Of course, you might wonder what happens if a vendor produces more than 65,000 different types of devices. Well, then they usually get another vendor ID so they can continue using it. So Linux might just have already some blacklist entry that tells the driver, okay, here I need to apply some special feature. And this can happen not only for USB devices, but for disks, for Ethernet devices, or even for something very stupid like UART, so a serial interface controller. That's something I'm currently fighting with on the RISC-V boards we have here, because these serial interfaces require special quirks. And you think that's one of the most standard things you have, but no, there's a bug in the hardware and you have to work around it quite significantly. Right, I'm getting a bit off track, so let's just continue with this. So in Unix, we have abstractions. So we've seen in Unix, everything, this is this Unix thing the Unix inventors actually tried to do. Everything is represented as a file. So even a device like a disk or a keyboard or whatever, a printer, is represented as something that looks like a file in your file system. These so-called special files, because they're not real files you could store data in, but they're working differently. These are usually contained in a special directory called /def for devices, but that's just a convention. You can put them anywhere you like. There's special system calls to create what we call device node. So essentially the special device called mknode, so make a node. And then you can actually create a device wherever you want. And the interesting thing, because everything's a file, this means reading and writing from a file works exactly the same as reading and writing from an I/O device, usually. So devices can be accessed using the same read and write operations you would need for regular files. So this means you also have to open them first, you should close them afterwards. And then if you open a special file, you essentially in the kernel create a connection for that file descriptor you're returned to the respective device. And this is then provided by the device driver for that file. So special files are identified also by a set of two numbers. So you have a major and a minor device number. So a major device number usually identifies the type of device, for example, a SATA disk. And then I don't have the numbers in my head, so you'd have to look them up. So there's usually a shell script called makedef that creates all these nodes for a new Linux installation or Unix installation. And so whenever there's a request, so you open this special device file, for example, /def/SDA1, then the major device indicates it's a SATA disk, for example, though that might also be a SCSI disk, but let's ignore this. It's a SATA disk in our case here. And then you might have several disks attached to your system. So the minor device number actually gives you the information which disk it is. So this is the first, second, third disk. And you can even go further. So SD, def SD would indicate the major device number. And then SDA, for example, would be the first disk, SDB the second. And then you can have partitions, which can also be encoded in the minor device number. So for example, you can have a minor device number of 0, which would indicate the first partition 1, the second, and so on and so forth. And then maybe 64 would go on with the second disk on that SATA controller. So this gives you something like a direct access to the driver by the user. Of course, that's not direct access, like without any access controls, but your operating system, of course, checks using standard Unix file permissions. Remember, it's just a file. So it checks if you are actually allowed to access this file. And of course, it handles errors and all that stuff. So handling everything as a file in Unix was a good idea until networks came along, and then it stopped working. Because networks, you've seen socket handling, work a bit differently. So essentially, you can also use read and write calls on them, opening a socket, reading from a socket, and everything works a bit differently. So the people who created Unix actually had subsequent projects, research projects at Bell Labs on creating operating systems like Plan 9 and Inferno, and these went much further. So in Plan 9, really everything is a file. Essentially, for example, your graphics card, so you can just send your graphics output to a special device representing your graphics card, and this is actually transparently transferred over the network to a different computer that actually displays the graphics. Something like that is entirely possible, and also with disks, with file systems, and so on. So Unix somehow stopped supporting this abstraction of everything as a file, and then these systems like Plan 9 and Inferno took it a bit further, but they never really caught on. Though if you want to experiment with them, both are available, for example, for a standard PC or a Raspberry Pi online on GitHub. You can download them, experiment with them. And the person who ported the Inferno operating system to the Raspberry Pi is actually a Russian engineer, but he lives in Trondheim for 20 years now, working in the embedded industry. And so he wrote a nice tutorial on how actually to port an operating system to a Raspberry Pi with the example of Inferno. So in general, everything's nevertheless a file if we're concerned with devices that are not network devices. And we distinguish between two general classes. So we have character-oriented devices. So these are devices which just deliver data one after the other, like a keyboard. You first press an A, then a B. So you first read an A, then a B out of it. And usually it makes no sense to position inside of a character device. So you can't say, I want this character that was typed 5 characters ago. That doesn't make sense. And that works for a large number of things like keyboards, serial interfaces, printers, audio devices, and so on. And then there's devices where you want to position your read-write position, so what we call seeking. So these include disk drives and SSDs, tape drives, floppy disks, CD-ROMs, and these are what we call block-oriented special files. So usually for, as the name says, for character-oriented special file or device, we read information character by character. So of course you can read multiple characters at once. And for block-oriented special files, these don't operate on single bytes, but on blocks of a minimal size, and usually of the same size. For example, disk drives commonly have a block size of 512 bytes. The more recent ones have 4 kilobytes, and CD-ROMs have 2 kilobytes block size, and so on. So for block-oriented special file, because this is much more efficient, always a complete block is transferred, though the driver also helps you abstract from this. And then we took a look at different methods of buffering. So we took a look at single buffering, a double buffering, and something that is required in the web server for the current practical exercise is a ring buffer. So a ring buffer is a very interesting data structure that's actually pretty simple, but details are maybe a bit tricky to implement somehow. So a ring buffer just means that you have, well, an array of buffers. And the important thing is that as soon as you reach the end, so you write one request after the other into your buffer, and as soon as you reach the end, you just start from scratch. This is usually done by having a base pointer to the first element, and then whenever you add something, you have a modulo operation on the address you write to. So at some point in time, when you reach the end of the buffer, you just return to the start again of your buffer. Of course, you have to take care not to overwrite elements in the buffer that have not been operated on. So we've seen these produce consumer problems, for example, and these ring buffers need synchronization. That's what you have to do in the practical exercise, obviously. And then we took a closer look at methods for I/O scheduling, especially important for disks or for devices where mechanical properties like real hard disks are relevant, like seek relay, like when you have to move the read-write head to a different track, and also rotational delay. So you have to wait a bit of time until the disk sector that you want to access rotates to be underneath your read-write head. And then we had a look at optimization criterion, so positioning time, for example, and we had to look at different algorithms like FIFO, shortest seek time first, and also the elevator algorithm, and had a look at and analyze the different properties for different requests. So usually I/O scheduling is a nice exam question, and we'll also have one on the theoretical exercise for this week. Right, another question came in. Then there's a bunch of extra stuff possible when a file is actually a terminal. I guess these are not devices these days, though. No, they are devices. Terminals are devices, but you can do a lot of additional things with, yeah, that's what I did go into detail. So in addition to doing reads and writes, so just transferring data from or to a device, you can also do things like I/O controls. So an I/O control is essentially a secondary channel to control properties of a device. For example, if you have a serial interface, the serial interface can have several different transmission speeds or baud rates, like a slow one like 9,600 or a faster one like 115,200. And you use read and write to actually transmit data to the device on the other end using a serial interface. And so you would need a different mechanism to actually configure, for example, the speed of that device. And this is done using these I/O controls. So there's a complete library for terminals using TC set attr and TC get attr to control attributes of a terminal. And so you use this I/O control as a separate method to actually configure essentially your device driver. Terminal handling, console handling in Unix is hardly complicated because Unix started off with just printing terminals. So essentially just a typewriter where you could type things. Those were sent to the computer and then printed on a sheet of paper in front of you, of course, an endless sheet of paper. And then you had the first video terminals, so a CRT and a keyboard attached, which just replaced the paper. And then we went through all these iterations of intelligent terminals where you could position cursors and stuff like that to draw primitive text-based user interfaces, like you might be used from like Norton Commander on DOS, if you've seen that before. I don't know, probably not. And finally, of course, we have graphical user interfaces where we have all these virtual terminals. So we have pseudo terminals. So each Xterm or each terminal.app on Mac OS X you open is a separate terminal that somehow behaves like a real terminal. So terminals have control codes, for example, for changing the font like to bold or reverse or underlined. Terminals have control code for positioning the cursor and so on. So essentially what your Xterm, for example, in Linux does, it actually emulates all of this. So that's why we call it a terminal emulator, because it just takes all these control sequences. So these are usually introduced by an escape character, so decimal 27 as ASCII code or hexadecimal 1B, and then some defined characters. There's different standards for this. The most common standard is what we call VT100 or ANSI nowadays. This is related to a real physical terminal from DEC, which is a VT100. Well, that wasn't surprising, right? I once had one. It was a pretty large beast, and it got really hot. So yeah, there's more modern terminals out there. And so essentially this has like almost 50 years of history behind it. So that's why I'm not detailing it in the course here, because that gets far too complicated. And even people experienced with Unix for decades can get confused by all this terminal handling stuff. So the notion of device also applies to non-physical things like pseudo-terminals as the next question. Yes, exactly. A pseudo-terminal is also just a device. So def PTY would be a pseudo-terminal, or if you have a text console on Linux, you have virtual consoles you can switch between. So also these might be just non-physical things, or you can also have a device for a RAM disk, which is also maybe not a physical thing. So a device is just anything you want it to be. So you could implement like there's a device for a pseudo random number generator, for example, def random, where you can just get random numbers out, and this is also not necessarily related to a physical device. Okay, another question is Xterm the terminal we usually see on Linux if the system uses the X Windows system? Yes. Another question, unfortunately, I have to answer with it depends. So Xterm is the standard terminal for the X Windows system. But if you have some graphical user interface like KDE or a GNOME version, then these come with their own terminals. So KDE has its K term with some extended features like different font selections and whatever, setting transparencies and backgrounds. X term is relatively primitive, and GNOME has the same with the GNOME term. So there's a large number of terminal emulators out there. So the X term was the original one, and then there was a bit more advanced one called RxVT. X term is relatively primitive, and don't try to read the X term code. I did, because I had to build a specialized terminal emulator when I was a student that required a special emulation for a specific terminal for a job I had. And I actually ended up manipulating RxVT instead of Xterm because I couldn't understand the Xterm source code. And I'm afraid it hasn't gotten any better in the last 25 years. So essentially, yeah, it really depends on what you configure when you open it. But you can see it when you type PS. So usually an Xterm is an Xterm, and a K term, a KDE term would be a K term, for example. Right. So you're going to get a new theoretical exercise. Sorry, I'm a bit delayed here, so it will appear like later this evening. And this will have a bit about real-time scheduling. Yeah, as I said, not relevant for the exam, but maybe you still want to have a look at it. And we will talk about I/O scheduling. This is definitely relevant for the exam. And I would guess, like most of my OS exams so far, I haven't written the exam yet, but most had an one question or one sub-question on I/O scheduling at least. So it's good to have a bit of an exercise on this. And of course, this is also important to know because I/O performance is highly relevant. Even if you have a fast I/O device, it's still an order or more of magnitude slower than what you have in than your computer or your main memory even. So essentially optimizing I/O performance is highly relevant because if you have an I/O bound system, your computer tends to get really, really slow. So that's why you usually have something like a buffer cache for your file system. But we're going to talk about this in this week's lectures about file systems. So that's why you usually try to keep a copy of the most recently accessed data in memory. So a cache for disk blocks, like a cache for memory contents that makes your CPU faster. So what we see here is scheduling is relevant not only for processes on a CPU, but I/O scheduling is another piece of scheduling that's relevant for the OS. All right. I guess that's all from my side today. Do you have any further questions? Any questions on the practical exercise so far? One of you got it to work so already? No, probably that takes a bit more. I'll stop recording now.